This is the second part of section 3. This one hopefully will be a little bit shorter for you. We've already looked at these first two objectives here, so let's take a look at the last two. We're going to, in this part, distinguish between theoretical yield, actual yield, and percentage yield, and of course we'll define each of those terms. And then we're going to calculate the percentage yield given actual yield and the quantity of a reactant. The theoretical yield is the maximum amount of a product that you can get in a given chemical reaction from a particular amount of a reactant. This is the amount, this is the quantity that you calculate using the table that we've been using. When you work down a column and back up another, you're actually calculating the theoretical yield, whether it be in moles or in grams. That is the theoretical yield. That's the maximum amount that you could get from that reaction. You usually don't get that much. And so what you actually, when you go in a laboratory and carry out the reaction, the actual yield is the amount that you really get. And there's a number of reasons for this. We'll cover those here in a little bit. But the actual yield is usually less, and it may be significantly less than the theoretical yield. The percentage yield is the ratio of actual to theoretical. In other words, it's the actual yield divided by the theoretical yield times 100 to make it a percentage. And so you see that equation here. Percentage yield equals actual yield divided by theoretical yield times 100.
In most chemical reactions, the amount of material produced is less than the theoretical or perfect yield. Separation and purification processes often result in the loss of some product. In some cases, more than one product can be formed in a reaction. In other cases, reactions may simply not go to completion or may undergo reverse reactions. In all these cases, less product is obtained than was predicted by the theoretical yield.
So let's take a look at a sample problem here. We have chlorobenzene, C6H5Cl, used in the production of things like aspirin, dyes, and disinfectants. One of the ways that you can make chlorobenzene is to react benzene, which is C6H6, with chlorine, and that's given in this equation here. Now we're actually told the problem we have when 36.8 grams of benzene reacts with an excess of Cl2, the actual yield of C6H5Cl is 38.8 grams. What is the percentage yield of C6H5Cl? Now if you think back to the problem, we said that percentage yield, and that's what we're being asked to calculate here, percentage yield is actual yield divided by theoretical yield. We don't know what the theoretical yield is. We're going to use the table to calculate that. One thing you need to be careful of is putting this, one of the biggest tendencies is to put this number here into the table and have 2 gram amounts. Don't do that. That's another thing that you absolutely must avoid. It's just going to cause confusion. So let's go and take a look at the solution to this problem. We have the equation here. I'll just rewrite the equation. C6H6 plus Cl2 yields C6H5Cl plus HCl. You see we get hydrochloric acid out of this. But first of all, let's just check and make sure this is balanced. We have 6 carbons on the left, 6 carbons on the right, 6 hydrogen on the left, and we have 5 plus 1 is 6 hydrogen on the left. We have 2 chlorine here, and 1 plus 1 is 2 chlorine there. Alright, let's go back and take a look. We have 36.8 grams of benzene and an excess of Cl2. That tells us that Cl2 will not be the limiting reactant. So we have 36.8 grams of the benzene, and we need to know what is the theoretical yield of the chlorobenzene. So we'll put our formulas in here. And now we're going to have to calculate the formula mass of the benzene, which is C6. So that's 12.0107 times 6 and 1.00794 times 6. So I get 78.1118 as my formula mass for that. For the C6H5Cl, that's C6, which is 12.0107 times 6 plus 5 times 1.00794 plus chlorine is 35.453, and I get 112.557. Okay, and both of these are grams per mole. Okay, so now I'm going to divide down and multiply up to get the grams of chlorobenzene. So 36.8 divided by 78.1118 divided by 1 times 1 doesn't do anything with it, times 112.557. And I get 53.027 to 3 sig figs. That's 53.0 grams. Okay, so the theoretical yield is 53.0 grams C6H5Cl. The actual yield I'll go back and just check that, was 38.8 grams. Okay, so our percentage yield is the actual yield, 38.8 grams, divided by 53.0 grams times 100, and I get 73.2%. Notice that that number is dimensionless. It is just 73.2%. That is the answer that we were looking for. That is our percentage yield. We're getting 73.2% of what we theoretically could get in this reaction. Okay, so that's what there is with that's the process of finding the percentage yield. You use the chart to calculate the theoretical yield, and the actual yield is usually given to you in the problem. Just make sure that you do not put this 38.8 grams in up here where we have to calculate the theoretical. That will just cause you confusion. You won't know which way to go because you're starting with a mass amount, and if you already have that one in there, it's very confusing. So avoid the temptation to put this in. We were told that that was the actual yield of the chlorobenzene. Okay, so don't put it in there. Don't put it. The actual yield does not go in the chart at all. The chart gives you the theoretical yield, and the actual yield just goes in on this formula. And that's the end.